Good day and welcome to our next topic, the rectangular coordinates. A fundamental goal of plane analytic geometry is the investigation of interesting and useful properties of configurations involving points, lines, and curves other than straight lines. Not only does the use of algebra contribute to the study of geometry, but geometric interpretations of algebraic equations and manipulations would give a better understanding of many phases of algebra. In this course, therefore, the knowledge of a few theorems and concepts from synthetic geometry will be used to give meaning and analysis of the figures represented by equations in its graph. Thus, knowledge about graphing is necessary. So the following will be discussed in our presentation today. For our rectangular coordinates, we will tackle about the directed line segment, position of a point in a surface, rectangular coordinates and units, distance between 2 points, midpoint of a line segment, division of a line segment, inclination and slope, parallel and perpendicular lines, angle between two lines, and area of a triangle. Directed line segments. When a line segment is measured in a definite sense from one endpoint to the other, the segment is said to be directed. A directed segment has a distance or length and direction. It is important to understand that the directed segment has a starting point referred to as the initial point. So taking for example our point A and point B, wherein we have a directed segment from A to B, also represented by the arrowhead. We have here, in the example, line segment AB is not equal to line segment BA because of the direction of the line. That is explained by when we say AB, the direction of our line is from A going to B. Now, by saying B to A, we are referring to B as our starting point. So, technically, your B to A is not equal from A to B. It is the line segment negative BA that is equal to line segment AB. By using a negative sign and interchanging the sequence of the points, we are defining the same segment to AB, giving us here our AB plus BA equal to 0, which is also from our second equation, AB equal to negative BA. So, it means that your AB here, directed to the right, is equal to your BA but negative. So your negative sign is giving an opposite direction to its sequence. So if our BA is from B to A but we add negative, so its direction now becomes opposite of your BA, which is the same now with your AB. If C is any third point of the straight line through AB as shown in the figures, our direction here is still going to the right, but it's just our C is either in between your point A and point B, or it is on the right of point B, or on the left of point A. For all possible positions of A, B, and C, in the first line, AB plus BC, wherein the sign is actually negative, that means we deduct this portion of the line. So here, we consider from point A to point B plus B to C, wherein your B to C is actually negative, will leave us with this portion alone. that is AC. For the second line, your A to B plus B to C, still directed to the right, is the same to line segment A to C. For the third point, your A to B, that is positive going to the right, plus BC, which is now your BC is negative because you are going opposite to the direction of the line segment, is equal to AC, which is your AC here is also negative because it's going to the left. Now, if we are to take the second equation here, line segment AB plus BC plus CA is equal to 0. So taking for example, the first line, your A to B plus B to C plus C to A, which is also negative, will give us 0 because our starting point A going to point B is just going back from B to C and C to A. So it's like in full sense, your BC and CA is the total opposite of your A to B. In your second line, that is also the same. So your A to B, positive to the right, plus B to C, still positive to the right, plus CA, which is now negative because your C to A is in opposite direction, is just equal. So giving the summation of the points equal to 0. In our third line here, that is A to B, B to C, plus C to A. So as you can observe, your AB here is positive, your CA here is also positive, but your B to C is negative, eliminating the total length of your line segment. So that is why our second equation here, AB plus BC plus CA, is equal to 0, which is true to all points or to all figures here. Therefore, two directed line segments lying in the same line or in parallel lines are said to be equal if and only if they have the same length or magnitude, they are of the same sense or direction. So based on our example earlier, our points AB and BC has the same line, the same length with our AC, but your AC is in different direction. So it's like your line segments are canceling each other, giving us a 0. Position of a point on a surface. If a point lies on a given surface, two magnitudes or coordinates are necessary to determine its position, each coordinate being measured in a definite sense. These coordinates may be rectangular coordinates or polar coordinates. Since our topic today is about rectangular coordinates, we will be focusing on it. Rectangular coordinates makes use of the Cartesian coordinate system in determining the position of a point on a surface, its coordinates being the x and y coordinates. So here we have the directed assumption of the Cartesian coordinate plane. So we have here two axes, the y-axis, which is the vertical, and the x-axis, which is the horizontal. Also, we have here four quadrants: quadrant 1, quadrant 2, quadrant 3, and quadrant 4. Each of them has their own combination of signs for x and y. So our rotation here is counterclockwise. So we always start with the upper right quadrant as our first quadrant. So this is the positive direction is upward and to the right. Here we have the origin, which has a coordinate of 0, 0. So from here, if you are going up, you are actually going into positive y-axis. If you are going right, this is positive x-axis. Opposite of those two axes, opposite in direction, will give us the negative direction, like this one. Going down will give us negative y-axis, and going to the left will give us the negative x-axis. In our first quadrant, the combination of the signs is positive x and positive y, because any point between or inside your quadrant 1 has positive x and positive y. In your second quadrant, since it is already on the left but still on the upper portion, you have there negative x and positive y. For your third quadrant, that is both negative x and negative y. For the fourth quadrant, you have now positive x but still negative y. Rectangular coordinates are written as ordered pair x and y. So your x coordinate or your abscissa is the perpendicular distance of a point from y-axis. So this is the value of your x coordinate, the point perpendicular from the y-axis. Now, your y coordinate or your ordinate is perpendicular distance from a point from the x-axis. So your y coordinate is located along your y-axis. So the location of your point based on the abscissa and the ordinate will be dependent also to the signs. So again, if positive x, it is on the right. If it is negative x, it is on the left. If it is positive y, it is upward. If it is negative y, it is downward. Let's take this one for an example. Here, our first example is a coordinate 2 and 3. So the first term here refers to your x coordinate. The second one is the y coordinate. Since our x coordinate is 2, so we will locate 2 in our x coordinate. Since it is positive, it is on the right. Your y coordinate is 3. So we will try to look for 3, and since this is positive, it is in the upward direction. So giving us here as the location of your point 2, 3. Another example, 1 and negative 5. Your x is 1, so this is positive, still on the right. Your y is negative 5, so we will move down. So 1 and negative 5. Our next example, negative 4 and negative 1. Both are negative. Our x coordinate is negative 4. So this one. Then our y coordinate is negative 1. So we will move down. So this is now the location of your -4 and -1. Your fourth example, -3 and 4. Your x is -3, so still on the left, 3. Then our y is 4, so we will move upward. So this is now the location of your fourth point. To acquire a more accurate graph of points, it is best to do the graphing on a graphing paper, of course. The scale could then be selected according to the nature of the drawings to be made. Distance between 2 points. Given 2 points, P1 with coordinates x1 and y1, and point 2 with coordinates x2 and y2, the distance between the points is given by this equation. Square root of x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. As you can remember from our previous discussion, your x here refers to the distance along x-axis, and your y is the distance along y-axis. And the distance between them, that is given by the formula D. Be sure to remember this one, since most of our problems will involve the computation of the distances between points. Taking for example this one, find the distance between the points 2 and 3, and 1 and -5, -3 and 4, and 2, 3, 2, 3, and -4 and -1, -4, -1, and 1, -5. I'm sure you are familiar with those points because we have this one as the same example in plotting your points in your Cartesian plane. Let's try to solve number 1. The distance between 2, 3 and 1, -5. So we are going to use the same formula, the distance formula. Square root of x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. So in our example here, your x sub 2 refers to the x coordinate of the second point, so that is 1, minus the x coordinate of the first point, which is 2. This one is the y coordinate of the second point minus the y coordinate of your first point. So by applying now your operations, 1 minus 2 will give us -1. -5 minus 3 will give us -8. Squaring will give us 1 and 64. So our answer here is square root of 65. So I want you to solve also for number 2, number 3, and number 4. And then you tell me if we have the same answers. For number 2, try to solve if you will get square root of 26. For number 3, you try to solve if you will get 2 square root of 13. And for number 4, try to solve if you will get square root of 41. Our next example show that the points P1 with coordinates 5, 0, P2 with coordinates 2, 1, and P3 with coordinates 4, 7 are vertices of a right triangle. So, we label the sides of the triangles as A, B, and C. A is the distance between points P3 and P2. B is the distance between the points P3 and P1. C is the distance between points P1 and P2. So we will solve the distances or the length of each side. For our side A, using the distance formula, our second point here is 4, 7. The first point is 2, 1. So, for the first term here, which is your x sub 2 minus x sub 1, the x coordinate of this point is 4. The x coordinate of this point is 2. For the y coordinate of this point is 7, and the y coordinate of this point is 1, which will give us an answer of, you use your calculator please, that is 2 square root of 10. For side B, this is your first point, this is your second point. So, the x coordinate of your second point is 4. The x coordinate of your first point is 5. Will give us 4 minus 5. For the y coordinate, the y coordinate of your second point is 7, and the y coordinate of your first point is 0. So you try to solve. The answer is 5 square root of 2. For our third point, this is our second point and this is our first point. So for our x coordinate, we have 2 and 5. For our y coordinate, we have 1 and 0. So you try to solve this one. And our leg C is equal to square root of 10. If the 3 points are vertices of a right triangle, they must make the Pythagorean theorem true. So in our example here, we will determine first which of the 3 sides are the legs and which one is the hypotenuse. So considering the values of our answers, which of these 3 has the longer length. Well, obviously, it is the line B, the one with the length 5 square root of 2. So, your line B is the hypotenuse, and your A and C are the legs. Now, we are gonna use the Pythagorean theorem, which will give us the formula b squared is equal to a squared plus c squared. Please do not be confused in using this formula. Always remember the concept that the square of the hypotenuse is equal to the sum of the square of its legs. At times, we will be using different notations, different symbols for our legs and for the hypotenuse, but always remember that the square of the hypotenuse is always equal to the sum of the squares of the legs. So, the common formula that we know is that c squared is equal to a squared plus b squared, wherein your hypotenuse is the letter c. But in our problem here, our hypotenuse is represented by letter b. So that is why we are using the formula b squared is equal to a squared plus c squared. So please do not be confused with that one. It is just a matter of notations or using symbols for it. Now, to solve for this one, we have 5 square root of 2 quantity squared, 2 square root of 10 quantity squared, plus square root of 10 quantity squared, which will give us 50 is equal to 40 plus 10, or that is 50 is equal to 50, which gives us a conclusion that it is a right triangle.